Hello, welcome to a continuation on our discussion about the electrostatic force. In the previous video on this topic, we talked about the electric force equation, which is this right here, just some constant multiplied by the product of two charges and divided by the square of the distance between them. And we drew a comparison between the electric force and the gravitational force, noting that there were some similarities in the structure of the equation. For example, both of the forces are inversely proportional to the square of the distance between them. Also, we drew like an analog between the mass and the charge in these two different force realms, and we actually determined that the force primarily responsible for the stability of atoms in the universe is the electric force due to this large K value, which we defined to be 8.99 times 10 to the ninth Newton meter squared per Coulomb squared, right? And then we also said that Q is defined as the charges on each of the individual particles, and then R is defined as the distance between the particles being analyzed. And to kind of just drive this review home a little bit, we looked at a system of two charges, and let's just give them positive 100 nanocoulomb charge each, and then separated by some distance of maybe like 1 centimeter or something like that. And the first thing to take note of is the likeness of the charges, right? So both of them are positive. If I call this particle A and this particle B, then I would say that the force on A due to B is acting to the left because it's repulsive. The geometric configuration that these charges in matters. Adversely, the force on B due to A is to the right because they're repulsive. Now this would be different if one of these was a negative charge, then we would have an attractive force case. And so that's what determines the direction of our force vector. It's not going to be the charges, because the geometric configuration of the charges and how they are located to each other relative in space is what determines the direction of the force. Okay, so with that review out of the way, we're now going to hop into the topic of today's video, which is going to be analyzing a system of 3 or more charges. And here I've just drawn a system of 3 charges. Okay, and just take a moment to look at this. We've got one positive charge at A, and then negative charges at locations B and C. And so we can tell right away that if we want to determine the net force on A due to both B and C, we can see that we're going to have an attractive force pulling A towards B and C. And so we're also not just dealing with charges in a line anymore. Now we have them in a plane. So we have to use vector arithmetic to break this down. We're going to have to use vectors to do this. And so I'll label my section here for the vector math. All right. And one thing we just determined is that the net force in the x direction is going to be positive, and the net force in the y direction is going to be negative, right? That was just given by the fact that A is going to be pulled towards both B and C, and they're both to the right and below. So we know that since A is going to be attracted to B and C, that it's going to be moving to the right and also down. We don't know by how much yet, but that's the whole purpose of our vector analysis. And so what I'm going to do is I'm going to just make the simple observation that the force on A due to these two particles, B and C, is just going to be, and I should write the force on A due to B plus the force of A due to the existence of C, the presence of C. Once we do this, we can just start writing our equations. So we'll say the net force on A, and I'm going to plug in our electric force equation, right? So we have K times QA, QB divided by, what's the position vector, right? We have two different position vectors involved. This one's going to be RAB, because those are the two charges that we're looking at for this term, and don't forget to square it. And then we do the same thing for charge C, and then some simplification is going to make this a lot easier to understand. And we can tell if a good idea is always to just kind of maybe isolate the particle. So let's say if I isolate particle A, right? So if I have particle A here, I can see from my diagram that the force due to B is going to be like in this direction. It actually has a slope of -2 on the graph, right? And so this is going to be force on A due to B, and then the one that is due to C has a slope of like -3. So that's like this. And so we have the sum of two forces on this particle A here. And we can see that by taking out all the other particles in the diagram, focusing on the one that we want to analyze, and then replace all of those particles with their associated forces. Okay, so back to our equation. So what we're going to have to do is break this up a little bit. So I'm going to rewrite this that is more vector friendly, in a form that is more vector friendly. And I'm going to factor out the QA because that seems to be a common term. And then that just leaves us with this expression QBR squared AB. Now we have to multiply by the unit vector, which is given by the position vector RAB, which we'll find in a second, divided by the magnitude of RAB, which we will also find here once we write this entire equation out. Okay, so we have this. We can do a little more simplification because we actually know that ooh, yeah. So this is going to be the sum of the x components. So the x force influence in the x direction due to these particles. Okay, and then I'm going to add a big bracket here, and then we'll do the second, we'll do the j components now. right? So these unit vectors here are going to tell us the direction that the force is acting. And as we simplify this more, it will become clear. So those are the components in the J direction. Now we've got this like super nasty expression. We probably want to simplify this for sure. We know that the unit direction vector is given by this little r hat, and that just equals the vector divided by its magnitude. Okay, so I'm going to replace all these terms in this equation with this right here. Now, this might seem weird because it's like, don't we need I and J components? Well, wrapped up in each of these, and you'll see this at the end, wrapped up in each of these direction vectors or these unit vectors is an X and Y component. But we're going to take note of one more thing before we actually evaluate this. We're going to say that, well, we know this from the thing. We're just going to call all of these Q, right? So that allows us to factor even more. So doing this final factoring step, we end up getting this simplified expression. Just much more compact, easier to move around and work with. And it kind of allows you to see the mechanics of the vector mathematics as applied to a real problem like this. So, all right, we've got our simplified expression for the sum of the forces on A. This is exactly what we need. Now we need to calculate the relative position vectors, right? So we've got to put values to all these R's, the RAB and the RAC. We've got to find the position vector, and then we've also got to find its magnitude, which will let us find the unit direction vector associated with AC and AB. So let's just do that right now. I'll label my section here, and we'll say that we're going to calculate relative position vectors, right? The distance between these particles is important. And remember I said at the beginning of the video, the geometrical configuration is very important. This is why. Vectors. All right, so let's just start with our points. We've got point A at 1, 2. We've got point B at 3, 1. And we've got point C at 2, negative 1. Okay. Start with AB. So the vector RAB is just point RB minus RA. Looking at that, we can easily see that this is the vector 2, negative 1. Might as well just calculate the magnitude as well. So the magnitude of vector RAB is equal to the square root of the sum of the squares. Pythagoras, thank you. And that's equal to the square root of 5. That's the magnitude of our vector RAB. RAC, same process. What do we got? So that's going to be RC minus RA. And that's going to equal 2 minus 1 and negative 1 minus 2, which is going to result in a vector of 1, negative 3. Again, taking the magnitude now of RAC. Same process, square root of the sum of the squares. That ends up being the square root of 10, right? So that's the magnitude of RAC. We're almost done. We are almost done. All we have to do now is just substitute into our equation, which we spent a great deal of time simplifying earlier. And I'm going to save even more time by just taking this and copying it and pasting it here. Good. Okay. So substitute our stuff into the equation. What do we have going on here? It looks like I'm just going to cross stuff out here and replace it. So we have 9 times 10 to the 9 times 100 times 10 to the negative 9 squared. Well, that's just 9e 2 minus 9 times 2 plus 9, right? And then 9e negative 5 is what we get for this first factored out term. RAB, what is that? Well, we said up there that is 2, negative 1. RAC is 1, negative 3. Oh, and don't forget, this is actually divided by the square root of 5. And this is divided by the square root of 10. So that's going to end up on the bottom here. Actually going to get an r cubed term, which is going to turn this. Well, so we know that RAB is square root of 5. Square root of 5 squared is 5, right? Same thing here. We know it's the square root of 10, so square that. This is 10. And then we're going to put these on the bottom with those in the next step. And I'll just do that right now. So this equals 9e negative 5 multiplied by, this is where those I and j components are. This is where they pop out. We'll put the, simplify all of our fractions while we go. 1, negative 3. This on the bottom is 10 square roots of 10. Whoops. Yes, this looks good. Okay, now keep in mind, we need to get this in terms of I and j, and we have those right here, right? So if we rearrange this around a little bit, we write our left-hand side. And I'm going to take this I component and this I component and group them together, and then I'm going to put this j component and this j component and group those together, since we can do that with fractions. And since these are both the I components, we can group them together as such. Now, all right, so we said that this thing is going in the negative direction, and we're actually getting, we've done it correctly so far, because we have both negative components here. Adding 2 negatives just makes positive. So what I'll do is I'll just put 1 over 5 times square root of 5 plus 3 over 10 square root of 10, and these are our j components. All that's left now is to just distribute this term here, right? And we can do this all in our heads. So we're gonna call this 18 e to the negative 5 over 5 square root of 5 plus, and then just continuing the distribution. All right, and that is that's our vector, right? If we wanted to find the magnitude of this vector, all we would have to do is we could call this the x component and the y component, and then we can just say that the magnitude of the force vector is just equal to the square root of x squared plus y squared, and then the angle that it's acting is actually going to be the inverse tangent of y over x. So you could write it in this polar form as well. Sometimes they'll ask you for this on your homework or on an exam. But I think this has been a fairly good demonstration of how to analyze the forces on a system of 3 or more charges regarding the electric force, the electrostatic force. So remember, we're just talking about particles here. These particles are influencing each other. Their presence attracts or repels one another. And depending on their geometric configuration and the sign likeness of their charges, this direction of the force vector can be determined, and then we can also find the magnitude of that force vector and the angle at which it is acting with respect to our horizontal axis. So with all that said, I hope this video was helpful. If there's anything you would like me to clarify, please leave it in the comments. Also, if there's anything you would like me to cover in the future, please leave that in the comments as well, and I would be happy to oblige. And with that said, have a wonderful weekend, and I'll see you in the next video.